Okay, let's give an overview of what's going to happen in this example TDK1, because there's a lot of moving parts and pieces, and it's going to be very easy to lose sight of what's going on. So let's give it some sort of essence of what's happening on the back end of all this. What we're really doing is trying to figure out how to represent the structure in what is this stiffness expression. The global stiffness matrix times the displacement vector is equal to the applied force vector. That's the ultimate thing that we're doing from a mathematical standpoint. We're going to use this particular interesting novel house that is a bridge across this little stream area, that the primary superstructure is a truss type system, and we're going to pull out that riser or vertical in that truss to motivate then these truss elements, right? And so we're going to approach assembling this structural stiffness matrix first through what we would call the generalized stiffness method, that's imposing then forces that create a very specific nodal displacement pattern. That's one way to do it, and it's a good way to physically understand, or rather understand physically, what the significance or the interpretation is of all these stiffness coefficients and what's going on with that. So we'll go all through that. Notice we ultimately end up with the same kind of expression here. These are just equilibrium equations where the unknowns are the displacements at the nodes, and we impose forces at the nodes. And so what are those displacements that are related to those imposed displacement pattern? And then we redo this in method 2 using the direct stiffness method, because of the simplicity that we can actually develop, or the simplistic way or direct way to assemble capital K is such that it's just perfect for computer programming. That's what we're going to go through this whole thing, and that's going to initiate then coming up with this little member stiffness matrix form that looks very much similar in the same kind of fashion as what we were doing before. And then how do we take that and put it into a global format from which then we can just do a direct superposition to get to the global stiffness matrix. And note again the sort of simplicity that's going to happen in this final form of just these individual stiffness coefficients that are then either just a minus sign away or a simple addition of things. That's that sort of perfect for the computer assembly approach that we're going to take. And then finally we apply it to the specific analysis of this system and get deep into how to manipulate those, and then back it back out into what it looks like for the overall structure and what's actually happening behind the scenes in the numerical solving routine in these computer structural analysis packages. Right? So that's what's going on, and now the individual parts will go through each of those little pieces that you just saw.